All right, ladies and gentlemen, this will be our last topic, and that is the heat of changing of states in Unit 6, Thermochemistry. So, in addition to energy being needed to raise the temperature of a substance, we were able to calculate that with our specific heat labs and problems that we have been doing. There's also different things that are going on, and that's when states of matter are changing, such as when you're going from a solid to a liquid and a liquid to a gas. And so when we have those, that is called the heat of fusion, meaning going from a solid to a liquid, or the heat of solidification, which is the opposite. And so they actually only tabulate one of those values. And so from there, it's just the negative because of one from the other. And you just have to kind of know what the value is and then what the other value is going to be for it. And so that's going to happen. And now these numbers are usually going to be pretty low because remember, the energy to kind of get those molecules moving, even though they are slightly moving, just moving just a little bit more doesn't take a lot of energy, but it does take a reasonable amount. Now, heat of vaporization or condensation, that's going to take usually a lot more energy, or a lot more energy is going to be released when this happens, because now you're trying to get the molecules moving fast enough to actually escape the liquid, the intermolecular bonds that are there within just the liquid form, so that it would then be in the gaseous form. And so that process actually takes a little bit more. So what does that mean? Well, then we have some of those going for us. And so we have some reactions that take just a little bit more to work, and therefore it's just a little bit harder. So as we kind of will see, we'll look at some of those values and that will make sense. And of course, heat of vaporization, the opposite of that would be the heat of condensation as well. Again, you have to pay attention to which one you're given and then also which one you need. That's a very important thing when moving forward. So as we can see in these diagrams, we have the heat of fusion moving up, and then the heat of vaporization. The heat of condensation is going down, and then the solidification goes also down as that's there. Now, a lot of times you're only going to be given certain values of these, and you can see that the heat of fusion values are fairly low, especially when compared to the heat of vaporization. One that doesn't make a whole lot of, that doesn't follow a complete suit is that of hydrogen, and that's because it doesn't take a lot of energy for hydrogen to go into the vapor stage, and it doesn't take a lot of energy for it to go into the liquid, from a solid to a liquid, because it's actually very hard to do the other opposite way from them because it gets pretty darn cold. Now, the values that we're going to use are the ones at the bottom there, for water being at 6.01 for the heat of fusion, and that's kilojoules per mole. And then for the heat of vaporization, it's 40.7. And so those are the values that we're going to deal with more often as we go through some of these examples and problems that we will look at, such as how many grams of ice at 0 degrees Celsius will melt, because again, when ice is melting, there really isn't much of a change in temperature. And so what we look at then is we just need to actually do some calculations for that. So how many grams of ice at 0 degrees will melt if 2.25 kilojoules of heat is added? Well, you have all the tools, and now we are just again giving you another tool to use in your stoichiometric problems. But here, no chemical reaction is being done, so it's just really just a conversion problem. And so what we see here is our 2.25 kilojoules. If I need to convert that into grams of something else, I have to use my heat of fusion, and that is my 6.01 kilojoules per mole, because again, when in doubt, convert to moles in chemistry, because it kind of gives you a lot of paths of where you could go with this. And so from here we can see their kilojoules would be canceled out. Now here's the other thing. I want grams of ice. Well, that means I need to know what the molecular mass of water is. Based on our previous experiences, we should know that it is about 18.01 grams per mole. Now the moles would then cancel out, giving us the label that we want. Now we can just do our math that we can do in our calculator, and we would see that we have a value of 6.75 grams of ice. Now that's not a lot of ice. It's actually a very little amount of ice. It's not even much of an ice cube, but it doesn't take much energy, and that energy can be easily supplied by your hand, the palm of your hand, as well. And that's why it doesn't take long for that nice sheet of ice on top of a lake to actually start to kind of show just a little bit of liquid when it starts to become sunny out in the springtime. And that's just kind of how that helps. As I mentioned before, that there is actually no change in temperatures, these little peaks that we see here. Now, some of you at the very beginning of the school year, when we did the lab of the states of matter and inquiry approach, you had solids in somewhere around here in their point value. They rose and then they kind of plateaued out. And some of them even see these little dips, and then it would plateau out. And then it rose fairly steadily. It was this next break that some of you just needed to get, and you only got to maybe here. But what you would see is that that plateau is very long, and it takes a lot of energy and actually to get it into this vapor stage. And that's when the temperature starts jacking back up again, and therefore the heat supplied. Now, you can actually kind of back calculate out how much methane, if you really wanted to. You could even figure out how much methane it takes to boil water, kind of doing this whole calculation, meaning if you have 2 cups of water, you would be able to have an idea, kind of knowing where it starts here, how much energy is going to needed to get it to boil. And then knowing from that, and knowing that the value of, say, methane has a heat of combustion value, you could actually calculate that out and see how close you are. Now, obviously, application of this would be a little bit off, but it's still kind of those things like you have that ability to do some of these just like crazy off the wall calculations that you know. So what does this mean? Well, now we have these abilities to kind of do some of these calculations. Well, what does that mean? It means that we need to be able to do some conversions of back and forth, and potentially even utilizing the heat equation for, say, specific heat. But this one here is just how much heat is absorbed. So it's just being absorbed from water at a liquid to convert it into steam, also at 100 degrees Celsius. Again, the value that we have here, that it's a constant pressure, is important for later units. And so here, again, we're going to utilize some things that we know. But here, we're going to start with something a little bit different, in that we're actually starting with a given amount of water. Now, it's not a lot of water, but it's water. And so, when in doubt, convert to moles. How would I convert grams into moles? Using the molar mass. Once I have it in the molar mass, I can then calculate to the amount of energy. And again, since I'm converting it to liquid to steam, so that'd be vaporization, I need to use a different value. And that would be my 40.7 kilojoules per mole. Now that I have those values done, I can do the rest of my calculations to see that it takes about 56.04 kilojoules to convert 25, roughly 25 grams or about 25 milliliters into steam. So it does take a lot, and it could, and that's why it doesn't take a much, and that's going to be even available somewhat at your ambient temperature. Now, there's some other values that will have to happen. Yes, there are the specific heat of water does change. It is 4.184 at 25 degrees Celsius. It does technically change. We'll worry about that later. So in a problem like this, it says convert 365 grams of steam at 175 degrees Celsius to ice at negative 50 degrees Celsius. Now, technically, there are some things that we would have to take into account, but just for, again, the sake of practice and knowing what we're doing, we are not going to worry about some of these what we actually would need to do. We're just going to utilize the 4.184. We're in high school. Just knowing that it is going to be a different value is going to be important. Now, how do we do this? Because that's going to be the other step, is how does this look? Well, I prefer sometimes to write out my problems of the kind of a plan, is that I'm going from 175 degrees Celsius to 100 degrees Celsius. Well, there's a phase transition there. Okay, so I'm going to need a delta H of that, and that would be of condensation. Then I'm going to take that 100 degrees and move it to 0 degrees Celsius. Now that is also a phase transition, and that is the phase transition going from a solidification. So my delta H of solid would be needed. Then I'm going to take it and go into a negative 50 degrees Celsius. Now, technically, this is going to have a different specific heat value, then this is going to have a different specific heat value, and this is going to have a different specific heat value. But we're not going to do it for this problem. So if you're watching this video and you need to do it, just understand that that's what it would be for. Okay? For the ease of use, we're going to make some things make our lives a little bit easier, because that's our theme of chemistry, is that Peterson's making our lives easier. And so when we find our delta T, we need to find our final minus 50 minus our initial, and that's of 175, to actually give us a delta T value of a negative 225 degrees Celsius. Now that we can take our starting mass of 365 grams times the specific heat of water. Again, we are going to be utilizing just that of water. We're not looking at doing it any other way. And then multiplying it by my negative 225 degrees Celsius. I multiply all of that up, and then I get a value, a very large value actually, of a negative, say 343,611 joules. That's not going to be useful for me because all my other values are going to need to be in kilojoules. And so I'm going to convert that into a negative 343.61 kilojoules. Now, that's only part of the story. So what do we need to do for that? I'm going to make this a little smaller so I can do some other work. When I do some of my other work, I'm going to see that I need to do some heat of vaporizations. Well, if I'm going to do those, I'm going to have to convert my grams into moles. And instead of doing it 2 times over, how about I just convert to moles once and utilize that value? And then I would have a value of 20.3 moles of H2O. Well, I will use that, and so if I take that and I go my 20.3 moles and I use my heat of condensation, and that would be a negative 40.7, because heat of vaporization is a positive. Opposite of that would give me the other, and that would be in kilojoules per mole. And since we multiply, our moles cancel out, and we get a value of a negative 100. Negative 121.8 kilojoules. Now, we are also going to utilize that 20.3 that we had calculated earlier of moles of water, and utilize the value. Oh, actually, that's the wrong value there. Oops. That is the wrong value. I was looking at the wrong value. That is a negative 824.85 kilojoules. Wow, that was a good thing I caught my mistake. And the heat of solidification is a negative 601, and so we have that, and when we multiply, the moles cancel out to give us a value of, and here's my negative 121.8 kilojoules. And so now if I add up those values that I have, I will get my answer of a negative 1,290.3 kilojoules of energy is being released when steam goes, we have about 365 grams of steam down to ice. And so there's a lot of energy that is released, because they has energy, and then as it condenses down, that energy has to be gone somewhere because the molecules slow down. So that's where you have that. Now you could do the same type of problem going the other way around, but again, it's nice to have and a good idea, highly suggested to follow suit and kind of utilize something like this when you kind of look like you're going through phase transitions, when you convert in your problems that you might do. Well, that concludes our talk of thermochemistry in Unit 6. Hopefully you are prepared. Feel free to look at any of the supplemental videos that I have made or have access to, and have added to our playlist for this class.